What if everything you thought you knew about space and reality was just the tip of the iceberg? In the strange and mysterious world of quantum mechanics, particles don't follow the rules we're used to. They can exist in multiple places at once, communicate instantaneously across vast distances, and even pass through barriers that should be impossible to cross. These aren't science fiction ideas, they're real phenomena that scientists are uncovering right now, and they're completely reshaping our understanding of the universe. From the bizarre behavior of entangled particles to the mind-bending concept of quantum tunneling, the discoveries we're about to explore will challenge your perception of space, time, and even reality itself. So buckle up, because by the end of this journey, you might just see the cosmos in a whole new light. Picture this: a beam of particles like electrons is fired at a barrier with two slits. On the other side, a screen records where these particles land. Simple enough, right? But here's where things get weird. If you don't observe the particles as they pass through the slits, they create an interference pattern on the screen, just like a wave would. It's as if each electron is passing through both slits at once, interfering with itself. But if you decide to watch the electrons as they travel, the interference pattern vanishes. Suddenly, the particles behave like tiny bullets going through one slit or the other, not both. This is the double-slit experiment, and it's one of the most jaw-dropping demonstrations of quantum mechanics. What's happening here? At the quantum level, particles like electrons don't behave like the solid objects we're used to. Instead, they exist in a kind of fuzzy, undefined state, a superposition, where they can act as both particles and waves. But the real kicker is this: it's the act of observation that forces them to choose how to behave. It's as if the universe is holding its breath, waiting for someone to look before deciding what's real. This isn't just a quirk of the experiment, it's a fundamental feature of reality itself. The observer isn't just a passive spectator, they're an active participant shaping the outcome. This duality, particles and waves, observer and observed, completely upends our classical understanding of space and reality. It's not just about tiny particles behaving oddly, it's about the nature of existence itself. The double-slit experiment shows us that at the most basic level, reality isn't fixed. It's fluid, malleable, and deeply interconnected with the act of observation. And if that doesn't make you question everything you thought you knew about the universe, well, just wait, because this experiment was only the beginning of the rabbit hole. What comes next is even stranger. Now, let's venture into one of the most perplexing and fascinating phenomena in quantum mechanics: quantum entanglement. Imagine two particles, perhaps electrons or photons, that become so deeply connected that the state of one instantly influences the state of the other, no matter how far apart they are. It's as if they're tied together by an invisible thread, communicating faster than the speed of light. This is entanglement, and it's so bizarre that even Albert Einstein famously called it spooky action at a distance. He was skeptical, convinced that there must be some hidden explanation, some missing piece that would restore order to the universe. But as it turns out, the universe doesn't play by the rules Einstein thought it should. Here's how it works: when two particles become entangled, they share a single quantum state. This means that if you measure one particle, say, its spin or polarization, the other particle's state is instantly determined, even if it's on the other side of the galaxy. It's not that the particle sends a signal, the information seems to be shared instantaneously, as if space and distance don't exist between them. This defies everything we know about classical physics, where nothing can travel faster than light. Yet experiment after experiment has confirmed that entanglement is real. In fact, researchers have successfully entangled particles over distances of hundreds of kilometers, proving that this spooky action is a fundamental part of nature. So, what does this mean for our understanding of the universe? For one, it suggests that space might not be as empty or disconnected as we think. Entangled particles seem to bypass the limitations of space-time, hinting at a deeper layer of reality where everything is interconnected. This has profound implications for fields like quantum communication and computing. Imagine a future where information can be transmitted instantaneously across the globe, or where computers harness the power of entangled particles to solve problems that would take classical computers millennia. We're already seeing the beginnings of this with quantum networks and encryption systems that rely on entanglement for unprecedented security. But entanglement isn't just a tool for technology, it's a window into the fundamental nature of reality. It challenges our intuition, forcing us to rethink what it means for objects to be separate or connected. And while Einstein may have been unsettled by its implications, modern science has embraced entanglement as a cornerstone of quantum theory. It's a reminder that the universe is far stranger and more interconnected than we ever imagined. And speaking of connections, this brings us to an even more mind-bending concept: quantum teleportation. But that's a story for the next chapter. Now, let's step into the realm of quantum teleportation, a concept that sounds like it belongs in a sci-fi movie, but is very much a reality in the quantum world. Unlike the teleportation we see in films, where objects or people vanish from one place and reappear in another, quantum teleportation doesn't involve moving anything physically. Instead, it's about transferring information, specifically the quantum state of a particle across vast distances instantaneously. It's a process that defies our everyday understanding of space and movement, and yet it's been achieved in laboratories around the world. Here's how it works. Imagine you have two entangled particles. Let's call them particle A and particle B. These particles are so deeply connected that whatever happens to one instantly affects the other, no matter how far apart they are. Now, suppose you want to teleport the quantum state of a third particle, particle C, to particle B. By performing a series of precise measurements on particle A and particle C, you can effectively transfer the state of particle C to particle B without ever physically sending it. The information doesn't travel through space, it simply reappears at the destination as if by magic. But it's not magic, it's the power of entanglement. This process relies on something called quantum superposition, where particles exist in multiple states at once until measured. By carefully manipulating these states and using entanglement as a bridge, scientists can teleport information from one place to another. It's a bit like sending a message through an invisible, instantaneous connection, one that doesn't care about the limitations of distance or time. And while this might sound abstract, it has very real implications for the future of technology. One of the most exciting applications of quantum teleportation is in secure communication. Because the information is transferred instantaneously and relies on entangled particles, it's nearly impossible to intercept or hack. This could revolutionize fields like cybersecurity, where protecting sensitive data is critical. Already, researchers have demonstrated quantum teleportation over distances of hundreds of kilometers, paving the way for a global quantum internet, a network where information is shared with perfect security and speed. But the potential doesn't stop there. Quantum teleportation could also play a key role in quantum computing, where processing power relies on the manipulation of quantum states. By teleporting these states between qubits, the quantum equivalent of computer bits, scientists could create more efficient and powerful quantum systems. It's a technology that could solve problems currently beyond the reach of classical computers, from simulating complex molecules for medical research to optimizing large-scale systems like traffic networks. Quantum teleportation isn't just a technical marvel, it's a glimpse into a deeper truth about the universe. It shows us that the boundaries of space and distance aren't as rigid as we once thought. At the quantum level, information can transcend the limits of classical physics, hinting at a reality where everything is more connected than we ever imagined. And as we continue to explore these possibilities, we're not just advancing technology, we're reshaping our understanding of what's possible, but the surprises don't end here. If quantum teleportation challenges our perception of space, what happens when we turn our attention to time? The next frontier in quantum mechanics might just rewrite the rules of how we experience the past, present, and future. What if time, the steady ticking of seconds we rely on every day, isn't as constant as it seems? In the quantum world, time can stretch, slow down, and even bend, defying our everyday experience of it. This isn't science fiction, it's a phenomenon rooted in both quantum mechanics and Einstein's theory of relativity, and it's been proven through some of the most precise experiments ever conducted. At the heart of this mystery is something called time dilation, a concept that reveals how time can flow differently depending on speed and gravity. And when we combine this with the bizarre behavior of quantum particles, we're left with a universe where time itself becomes fluid and unpredictable. Take atomic clocks, for example. These aren't your average wall clocks. They're some of the most accurate timekeeping devices ever built, capable of measuring time down to the billionth of a second. Scientists have used these clocks to test Einstein's predictions about time dilation, and the results are nothing short of astonishing. In one famous experiment, researchers placed two atomic clocks at different elevations, one on the ground and one on a high-altitude airplane. After the plane landed, they compared the two clocks and found that the one on the plane, which experienced slightly weaker gravity, had ticked ever so slightly faster than the one on the ground. Time itself had slowed down for the clock closer to Earth's gravitational pull. This might seem like a tiny difference, but it's proof that time isn't a fixed, universal constant. It's a flexible, dynamic force shaped by the environment. But here's where it gets even stranger. In the quantum realm, time dilation takes on a whole new layer of complexity. Imagine a particle moving at near light speed or existing in an intense gravitational field. From our perspective, time for that particle would slow down dramatically, but from the particle's perspective, time might feel completely normal. This isn't just a thought experiment, it's a real effect that has been observed in particle accelerators, where particles traveling at incredible speeds appear to live longer than their stationary counterparts. It's as if time itself is bending to accommodate the quantum world's rules. This interplay between quantum mechanics and relativity shatters our classical understanding of time as a straight, unbroken line. Instead, time becomes a malleable fabric woven together by the forces of speed, gravity, and the quantum state of particles. And if that weren't mind-bending enough, some theories even suggest that particles at the quantum level might not experience time in the same forward-moving direction we do. In fact, certain experiments hint at the possibility of particles moving backward in time, a concept that could revolutionize our understanding of cause and effect. So, what does all this mean for us on a practical level? These discoveries have already transformed technology. GPS systems, for instance, rely on atomic clocks that account for time dilation caused by Earth's gravity and the satellite's high speeds. Without this adjustment, your GPS would be off by miles within minutes. But on a deeper level, these findings challenge us to rethink our place in the universe. If time isn't the steady, unchanging force we've always believed it to be, what else about reality might be more fluid than we realize? As we continue to explore the mysteries of time dilation and quantum clocks, we're not just uncovering the secrets of the universe, we're also reshaping how we perceive existence itself. And with every discovery, we're reminded that the cosmos is far stranger and more interconnected than we ever imagined. But the journey doesn't stop here. What if particles aren't just moving forward and backward in time? What if they exist outside of it entirely? That's where the next chapter of this quantum adventure begins. What if there were particles that could move backward in time? It might sound like the plot of a science fiction movie, but in the world of quantum physics, this idea isn't just possible, it's predicted by the math. And it all ties into one of the most mysterious substances in the universe, antimatter. You've probably heard of antimatter as the mirror image of ordinary matter, but there's far more to it than just its explosive potential. Antimatter holds clues to one of the most profound questions in physics. Does time always flow forward, or can it reverse under certain conditions? Let's break this down. Every particle of matter we know, electrons, protons, quarks, has an antimatter counterpart. These antimatter particles have the same mass as their matter twins but opposite charges. For example, the antimatter version of an electron, called a positron, has a positive charge instead of a negative one. When matter and antimatter meet, they annihilate each other in a burst of energy. This symmetry between matter and antimatter is one of the universe's most elegant features, but it also raises a fascinating question. If matter and antimatter are so similar, why is our universe dominated by matter? Where did all the antimatter go? Scientists are still searching for answers, but one clue might lie in the way antimatter behaves with respect to time. In quantum field theory, there's a concept called CPT symmetry, which stands for charge parity and time reversal symmetry. This principle suggests that if you flip a particle's charge, mirror its spatial coordinates, and reverse the direction of time, the laws of physics should remain the same. In other words, antimatter can be thought of as ordinary matter moving backward in time. This isn't just a theoretical idea, it's been supported by experiments. For instance, researchers at CERN have been studying antihydrogen, the antimatter counterpart of hydrogen, to see if it behaves differently under the influence of gravity or other forces. So far, the results suggest that antimatter follows the same physical laws as matter, but the time reversal aspect remains one of the most intriguing mysteries. The implications of this are staggering. If antimatter truly represents matter moving backward in time, it could mean that time itself isn't as one-directional as we think. Imagine a particle traveling forward in time while its antimatter counterpart moves backward. From our perspective, the antimatter particle would appear to defy the arrow of time, creating a kind of temporal symmetry that challenges our understanding of cause and effect. This idea isn't just a thought experiment, it has practical implications for how we study the universe. For example, understanding antimatter could help us unlock the secrets of the Big Bang, when matter and antimatter were created in equal amounts. Why matter won out over antimatter is one of the biggest unsolved puzzles in cosmology, but the story doesn't end there. Experiments at facilities like CERN are pushing the boundaries of what we know about antimatter. By creating and trapping antihydrogen atoms, scientists are able to study their properties in unprecedented detail. These experiments aren't just about satisfying curiosity, they're about testing the very foundations of physics. If antimatter behaves differently than predicted, it could mean that our current theories are incomplete, opening the door to entirely new ways of understanding reality. So, what does all this mean for our perception of time? If particles can move backward in time, even in theory, it suggests that the universe is far more flexible and interconnected than we ever imagined. Time might not be the rigid, forward-flowing river we experience in our daily lives. Instead, it could be a dynamic, reversible force shaped by the behavior of particles at the quantum level. And as we continue to explore the mysteries of antimatter, we're not just uncovering the secrets of the cosmos, we're redefining what it means to exist within it. But the quantum world isn't done surprising us yet. If particles can move backward in time and annihilate their counterparts, what happens when they encounter barriers that should be impossible to cross? That's where the phenomenon of quantum tunneling comes into play, a concept that bends the rules of space and energy in ways that seem almost magical. Stay tuned, because the next chapter of this quantum journey is about to take us even deeper into the unknown. Now, let's dive into one of the most baffling yet fascinating phenomena in quantum mechanics: quantum tunneling. Imagine standing in front of a solid brick wall. According to everything we know about classical physics, there's no way you could pass through it without breaking it down or climbing over it. But in the quantum world, particles don't always follow these rules. They can do something that seems downright impossible. They can pass straight through barriers that should be completely impenetrable. This is quantum tunneling, and it's not just a theoretical curiosity. It's a fundamental process that shapes the universe and powers some of the most advanced technologies we use today. So, how does quantum tunneling work? At the heart of this phenomenon is the idea that particles like electrons don't have definite positions until they're observed. Instead, they exist as waves of probability spreading out in space. When one of these waves encounters a barrier, like an energy wall, it doesn't just stop dead in its tracks. Instead, there's a small but real chance that the particle will tunnel through the barrier and appear on the other side. It's as if the particle briefly borrows energy from the universe, slipping through an invisible doorway that classical physics says shouldn't exist. This isn't magic, it's the strange, counterintuitive nature of quantum mechanics at work. One of the most awe-inspiring examples of quantum tunneling happens every second in the heart of stars, including our own sun. Nuclear fusion, the process that powers stars, relies on protons overcoming their natural repulsion to fuse together and release energy. But here's the catch: the energy required to push protons together is immense, and under normal circumstances, they shouldn't be able to get close enough to fuse. That's where quantum tunneling comes in. Thanks to this phenomenon, protons can tunnel through the energy barrier that separates them, allowing fusion to occur and stars to shine. Without quantum tunneling, the universe as we know it wouldn't exist, but the implications of quantum tunneling go far beyond the cosmos. In our everyday lives, this phenomenon plays a crucial role in modern technology. Take transistors, for example, the tiny switches that form the backbone of every computer and smartphone. Transistors rely on electrons tunneling through barriers to control the flow of electricity, enabling the rapid processing of information that powers our digital world. Similarly, flash memory, the technology used in USB drives and solid-state drives, depends on quantum tunneling to store and retrieve data. These devices wouldn't work without the bizarre behavior of particles at the quantum level. What's truly mind-blowing about quantum tunneling is how it challenges our understanding of space. Classically, we think of space as a fixed, impenetrable structure, a stage where particles move around like actors. But quantum tunneling shows us that space is far more dynamic and permeable than we ever imagined. Barriers that seem insurmountable in the classical world become mere speed bumps in the quantum realm. This raises profound questions about the nature of reality itself. Is space truly empty, or is it filled with hidden pathways and possibilities that we're only beginning to uncover? As we continue to explore the mysteries of quantum tunneling, we're not just unlocking new technologies, we're also redefining our understanding of the universe. It's a reminder that the boundaries we take for granted might not be as solid as they appear. And this brings us to an even more intriguing question. If particles can tunnel through barriers, what does that mean for the concept of nothingness? Is empty space truly empty, or is it teeming with activity we can't yet see? The answers to these questions could reshape our understanding of reality in ways we can't yet imagine. Let's take a closer look at the quantum vacuum, a concept so strange, it turns everything we thought we knew about empty space on its head. When we think of a vacuum, we imagine a vast, empty void, a place where nothing exists. But in the quantum world, nothing is far from empty. In fact, space is alive with activity, a seething sea of energy and particles that flicker in and out of existence faster than the blink of an eye. This is the quantum vacuum, and it's one of the most profound discoveries in modern physics. At the heart of this idea is something called zero-point energy. Even in a perfect vacuum where all matter and energy have been removed, there's still a tiny, irreducible amount of energy left behind. It's like the hum of an engine that never turns off, a background buzz that permeates the fabric of space. This energy isn't static. It's constantly giving rise to pairs of virtual particles, particles that appear out of nowhere, exist for a fleeting moment, and then vanish back into the void. These particles aren't just theoretical, they've been detected indirectly through their effects on the behavior of atoms and light. It's as if the universe is a stage, and these virtual particles are actors who appear, deliver a single line, and then disappear before the audience even notices. This constant dance of creation and destruction challenges our classical notion of empty space. Instead of a barren, lifeless expanse, the quantum vacuum is a dynamic, energetic field filled with potential and possibility. It's a reminder that the universe is far more active and interconnected than we ever imagined. And this isn't just a curiosity, it has profound implications for our understanding of the cosmos. One of the most exciting areas where the quantum vacuum plays a role is in the search for dark energy. Astronomers have discovered that the universe is expanding at an accelerating rate, driven by a mysterious force that seems to permeate all of space. This force, known as dark energy, could be linked to the energy of the quantum vacuum. If the vacuum is filled with zero-point energy, it's possible that this energy is contributing to the expansion of the universe, pushing galaxies apart faster and faster over time. It's a tantalizing idea, but one that comes with its own set of challenges. The energy density predicted by quantum theory is vastly larger than what we observe in the universe, leading to what's known as the cosmological constant problem, a puzzle that physicists are still working to solve. But the quantum vacuum doesn't just shape the universe on the largest scales, it also influences the behavior of particles on the smallest. For example, the Casimir effect, where two uncharged metal plates placed close together in a vacuum experience an attractive force, is a direct consequence of the quantum vacuum's energy. This effect, first predicted in the 1940s and later confirmed by experiments, shows how the vacuum's activity can have tangible, measurable consequences. It's a vivid demonstration that even in the emptiest regions of space, there's more going on than meets the eye. As we continue to explore the mysteries of the quantum vacuum, we're not just uncovering the secrets of space, we're also redefining what it means for something to be empty. This dynamic, energetic field challenges us to rethink our most basic assumptions about the universe. And as we peel back the layers of this cosmic mystery, we're led to an even more astonishing idea that the universe itself might be a hologram. But that's a story for the next chapter of this quantum journey. What if the universe we see around us, the stars, planets, and galaxies, isn't as solid and three-dimensional as it appears? What if it's more like a hologram, a projection of information encoded on a distant surface? This isn't just a wild idea from science fiction. It's a serious scientific theory known as the holographic principle. At its core, the holographic principle suggests that all the information contained within a volume of space can be represented as a two-dimensional surface, much like a hologram. In other words, the three-dimensional world we experience might just be a kind of cosmic illusion, a projection of data stored on the boundaries of space itself. It's a concept that flips our understanding of reality on its head, and it has profound implications for how we think about space, black holes, and the very fabric of existence. The roots of the holographic principle trace back to the study of black holes, those enigmatic regions of space where gravity is so intense that not even light can escape. In the 1970s, physicist Jacob Bekenstein discovered that the entropy, or disorder of a black hole, is proportional to the area of its event horizon, the boundary beyond which nothing can return. This was a surprising result because in most physical systems, entropy is related to volume, not surface area. Building on this idea, physicist Leonard Susskind and others proposed that the information about everything that falls into a black hole isn't lost but is instead encoded on its event horizon. This led to the radical idea that the information in any region of space could be represented as a hologram on its boundary, challenging the notion that our universe is fundamentally three-dimensional. At first glance, this might sound like an abstract mathematical curiosity, but the holographic principle has far-reaching implications. For one, it suggests that the universe might be far simpler than it appears. Instead of storing information in every point of three-dimensional space, the universe could encode everything on a two-dimensional surface, like a cosmic hard drive. This idea aligns with quantum mechanics, which shows that particles and energy are fundamentally quantized or broken into discrete units. The holographic principle takes this a step further, proposing that even space itself might be built from these quantized bits of information. It's a bit like realizing that the rich, detailed world of a video game is actually generated from a flat, two-dimensional code, a code that holds all the complexity we experience. But what does this mean for our perception of reality? If the universe is a hologram, then the three-dimensional world we see and touch might be a kind of projection, a way for our brains to interpret the underlying information. It's a bit like watching a movie on a screen. The images seem to have depth and motion, but they're actually created by a flat, two-dimensional surface. This idea challenges our intuition, forcing us to reconsider what it means to exist in space. It also raises fascinating questions about the nature of black holes. If the information about everything that falls into a black hole is encoded on its event horizon, then black holes might not be the destructive voids we once thought. Instead, they could be the ultimate information storage devices, preserving the data of the universe in a way we're only beginning to understand. The holographic principle isn't just a theoretical curiosity, it's a tool that could help us solve some of the biggest mysteries in physics. For example, it offers a potential bridge between quantum mechanics and general relativity, two theories that describe the universe at vastly different scales but have proven notoriously difficult to reconcile. By treating space as a holographic projection, physicists might find a way to unify these theories, creating a more complete picture of reality. It's a bold idea, but one that's backed by rigorous mathematics and growing experimental evidence. As we peel back the layers of this cosmic mystery, we're left with a profound realization. The universe might be far stranger and more interconnected than we ever imagined. The holographic principle invites us to see reality not as a fixed three-dimensional stage, but as a dynamic, information-rich projection, a cosmic dance of data that shapes everything we experience. And as we continue to explore this idea, we're led to an even more intriguing question. If the universe is a hologram, what role does consciousness play in shaping it? That's where our journey takes us next, into the fascinating intersection of quantum mechanics and the human mind. What if the very act of looking at the universe changes it? This isn't just a philosophical musing. It's a question that lies at the heart of one of the most heated debates in modern physics. At the intersection of consciousness and quantum mechanics, we find a profound and controversial idea: that the observer plays a crucial role in shaping reality. It's a concept that challenges our deepest assumptions about the universe and raises questions that blur the line between science and philosophy. Does consciousness have the power to influence the quantum world? And if so, what does that mean for our understanding of existence? This idea stems from one of the earliest interpretations of quantum mechanics, the Copenhagen interpretation. Developed in the 1920s by physicists like Niels Bohr and Werner Heisenberg, this framework suggests that particles exist in a state of superposition, meaning they can be in multiple states at once until they're observed. The moment someone takes a measurement, the particle's wave function collapses, forcing it to choose a single state. In other words, the act of observation seems to determine what becomes real. It's as if the universe is a cosmic stage and the observer is the director, deciding how the scene unfolds. But this raises an intriguing question: what counts as an observer? Is it a human being, a machine, or something else entirely? This is where the debate gets heated. Some physicists argue that consciousness itself is the key, that the mind somehow interacts with the quantum world to collapse the wave function. Others dismiss this idea as speculative, pointing out that measurement devices can collapse the wave function just as effectively as a human observer. The truth is, we don't yet have a definitive answer, but the question of whether consciousness plays a role in shaping reality has sparked intense discussions among scientists, philosophers, and even spiritual thinkers. One of the most fascinating experiments to explore this idea is the delayed choice quantum eraser. In this setup, particles are sent through a maze of mirrors and detectors with their paths recorded. But here's the twist: the decision about whether to measure the particle's path is made after the particle has already passed through the maze. Astonishingly, the results suggest that the observer's choice in the present can retroactively influence the particle's behavior in the past. It's as if the universe is rewriting its own history based on what we decide to measure. While this doesn't necessarily prove that consciousness is involved, it does hint at a deeper connection between observation and reality, one that we're still struggling to understand. The implications of this debate are staggering. If consciousness does play a role in shaping quantum reality, it could mean that the universe is far more interactive and subjective than we ever imagined. It challenges the notion of a purely objective reality, suggesting instead that reality might be co-created by the act of observation. This idea has profound consequences not just for physics, but for how we see ourselves in the cosmos. Are we passive witnesses to the universe or active participants in its unfolding? As we grapple with these questions, it's important to remember that this is still a frontier of science. The relationship between consciousness and quantum mechanics remains one of the most enigmatic and controversial topics in physics. But what's clear is that the act of observation, whether by a human, a machine, or something else, has a profound impact on the quantum world. And this brings us to another mind-bending concept: quantum superposition, where particles can exist in multiple states at once, defying our classical understanding of reality. But that's a story for the next chapter of this quantum journey. Now, imagine a world where a single object can be in two places at once, or a particle can spin in two opposite directions simultaneously. Sounds like science fiction, doesn't it? But in the quantum realm, this is not only possible, it's a fundamental feature of reality. This is the concept of quantum superposition, where particles exist in multiple states at the same time until they're observed. It's one of the most mind-bending ideas in physics, and it completely shatters our classical understanding of how the universe works. To help wrap our heads around this, let's turn to a famous thought experiment: Schrödinger's cat. Imagine a cat sealed inside a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter detects it, triggering the release of the poison and killing the cat. If it doesn't decay, the cat lives, according to quantum mechanics, until someone opens the box and observes the system. The atom is in a superposition of both decayed and not decayed states. This means the cat is simultaneously alive and dead, a paradox that highlights the strangeness of superposition. Of course, in the real world, we don't see cats in such bizarre states, but this metaphor helps us grasp how quantum particles behave when we're not looking. So, what's really happening here? At the quantum level, particles like electrons or photons don't have definite properties until they're measured. Instead, they exist in a kind of fuzzy, probabilistic state where all possible outcomes coexist. It's only when we observe them that this superposition collapses and the particle chooses a single state. This isn't just a quirk of the math, it's a fundamental aspect of nature that has been confirmed by countless experiments. For example, in the double-slit experiment, particles behave as if they're in multiple places at once, creating an interference pattern that only makes sense if they're in superposition. But superposition isn't just a theoretical curiosity, it's the foundation of some of the most groundbreaking technologies of our time. Take quantum computing, for instance. Classical computers use bits that can be either a 0 or a 1, but quantum computers use qubits, which can exist in both states simultaneously thanks to superposition. This allows quantum computers to perform many calculations at once, solving problems that would take classical computers centuries to crack. From simulating complex molecules for drug discovery to optimizing global supply chains, the potential of quantum computing is staggering, and it all hinges on the strange behavior of particles in superposition. The implications of superposition go far beyond technology, though. It forces us to rethink our understanding of reality itself. In the classical world, objects have definite properties. A chair is either here or there, a light is either on or off. But in the quantum realm, the rules are different. Reality seems to be fluid, a tapestry of possibilities that only solidifies when observed. This raises profound questions. What does it mean for something to be real? Is the universe fundamentally uncertain, or is there a deeper order we're only beginning to uncover? As we delve deeper into the mysteries of superposition, we're not just exploring the behavior of tiny particles, we're challenging the very foundations of physics. It's a reminder that the universe is far stranger and more wondrous than we ever imagined. And this brings us to an even more intriguing question. If particles can exist in multiple states at once, what happens when we try to measure them more precisely? That's where the Heisenberg uncertainty principle comes into play, and it's the next chapter in our quantum journey. Now, let's explore one of the most pivotal moments in quantum mechanics, the collapse of the wave function. Picture a particle like an electron, existing in a haze of possibilities, multiple positions, multiple states, all at once. This is the essence of the wave function, a mathematical description that captures all the potential outcomes for a quantum system. But here's the catch. The moment we measure or observe the system, that cloud of possibilities collapses into a single, definite state. It's as if the universe, faced with a question, suddenly decides on an answer. This transition from probability to reality is one of the most profound and perplexing features of quantum mechanics, and it completely upends our classical understanding of how the universe operates. In the classical world, we're used to thinking of reality as fixed and deterministic. If you know the starting conditions of a system, like the position and speed of a ball, you can predict exactly where it will land. But in the quantum realm, this certainty vanishes. Until an observation is made, particles don't have definite properties. They exist in a superposition of states, a kind of quantum limbo where all possibilities are equally real. The act of measurement forces this superposition to collapse, selecting one outcome from the many. It's like rolling a dice, but the dice only lands on a number when you look at it. This collapse challenges the very foundation of determinism, the idea that every event is governed by cause and effect. Instead, quantum mechanics suggests that at the most fundamental level, the universe is governed by probability. It's not that we lack the tools to predict outcomes, it's that the outcomes themselves are inherently uncertain until observed. This idea was so unsettling to some physicists like Albert Einstein that he famously declared, "God does not play dice with the universe." Yet, decades of experiments have confirmed that the universe does, in fact, operate this way. But what exactly causes the wave function to collapse? This question has sparked intense debate and led to some fascinating interpretations. One of the most well-known is the Copenhagen interpretation, which suggests that the act of observation itself triggers the collapse. In this view, the observer, whether a human, a machine, or any measuring device, plays a crucial role in shaping reality. It's a perspective that blurs the line between the observer and the observed, suggesting that the universe is far more interactive than we ever imagined. Another compelling interpretation is the many worlds theory, which takes a radically different approach. Instead of the wave function collapsing into a single outcome, this theory proposes that every possible outcome actually happens, but in parallel universes. In other words, when you measure a quantum system, the universe splits into multiple branches, each corresponding to a different outcome. Your observation doesn't collapse the wave function. It simply places you in one of countless parallel realities. It's a mind-bending idea that suggests our universe is just one thread in an infinite tapestry of possibilities. These interpretations raise profound questions about the nature of space and time. If the wave function collapses into a single outcome, does that mean reality is shaped by our observations? Or if the many worlds theory is correct, are we constantly branching into new realities with every quantum event? Both ideas challenge our intuitive sense of how the universe works, suggesting that the fabric of reality is far more dynamic and interconnected than we ever imagined. As we grapple with these questions, it's important to remember that the collapse of the wave function isn't just a theoretical puzzle, it's a practical reality. It underpins the behavior of particles in experiments, the functioning of quantum computers, and even the processes that power the stars, but it also leaves us with more questions than answers. What happens to all those other possibilities when the wave function collapses? Do they simply vanish, or do they continue to exist in some form? And if observation plays such a crucial role, where exactly do we draw the line between the observer and the observed? These questions lead us to another fascinating phenomenon, quantum decoherence, a process that helps explain why the quantum world doesn't always seem so strange in our everyday lives. It's a concept that bridges the gap between the quantum and classical realms, offering new insights into how probability becomes reality. But that's a story for the next chapter of this quantum journey. So, if particles can exist in multiple states at once, why don't we see cats that are both alive and dead, or chairs that are in two places at the same time? Why does the quantum world seem so bizarre, while the world we experience every day feels solid and predictable? The answer lies in a fascinating process called quantum decoherence, a phenomenon that bridges the gap between the strange, probabilistic nature of quantum mechanics and the familiar, deterministic world we live in. At its core, quantum decoherence is about how quantum systems lose their superposition when they interact with their surroundings. Imagine a particle in a superposition of two states. Let's say it's spinning both clockwise and counterclockwise at the same time. In isolation, this particle can happily exist in this fuzzy, undefined state. But the moment it interacts with something in its environment, a stray photon, a passing atom, or even the air molecules around it, that interaction measures the particle, forcing it to choose a single state. The result, the superposition collapses and the particle starts behaving like a classical object. It's as if the environment is constantly observing the particle, chipping away at its quantum weirdness until it's gone. This process explains why we don't see quantum effects in our everyday lives. In the microscopic world of atoms and particles, interactions are rare enough that superpositions can survive for a while. But when you scale up to larger objects like a cat or a chair, the sheer number of interactions with the environment becomes overwhelming. Each collision, each exchange of energy, acts like a tiny measurement, collapsing the superposition bit by bit until the object settles into a single classical state. It's not that quantum mechanics stops working at larger scales. It's just that the environment is constantly nudging quantum systems toward classical behavior. But quantum decoherence isn't just a theoretical curiosity. It has real-world implications, especially in the field of quantum computing. Quantum computers rely on maintaining superpositions to perform calculations, but decoherence can disrupt these delicate states, causing errors and limiting the computer's power. To combat this, scientists are developing techniques like quantum error correction and isolating quantum systems in ultra-cold, vacuum-sealed environments. These efforts are pushing the boundaries of what's possible, but they also highlight just how challenging it is to preserve quantum coherence in a world that's constantly trying to erase it. Perhaps the most profound implication of quantum decoherence is what it tells us about reality itself. In the quantum world, reality is fluid and uncertain, a tapestry of possibilities. But as systems grow larger and more complex, decoherence smooths out this uncertainty, giving rise to the stable, predictable world we experience. It's as if the universe has a built-in mechanism for transitioning from quantum strangeness to classical order. This raises deep questions about the nature of reality. Is the classical world just an approximation, a simplified version of a much more complex quantum reality? And if so, what does that mean for our understanding of existence? As we unravel the mysteries of quantum decoherence, we're not just learning how quantum systems behave, we're gaining insights into the very fabric of reality. It's a reminder that the universe operates on multiple levels, from the microscopic to the cosmic, each with its own set of rules. And this brings us to another cosmic mystery, one that lies at the intersection of quantum mechanics and gravity, the quantum nature of black holes. What happens when the strangeness of quantum mechanics meets the extreme gravity of a black hole? The answer might just rewrite the rules of physics as we know them. Now, let's venture into one of the most enigmatic frontiers of modern physics, the collision of quantum mechanics and black holes. These cosmic giants, with their unimaginable gravitational pull, have long been a source of fascination and mystery. But when we combine the strange rules of quantum mechanics with the extreme environment of a black hole, we uncover a paradox that challenges everything we think we know about space, time, and even the nature of reality itself. This is the story of Hawking radiation, the information paradox, and the quest to unravel one of the universe's greatest mysteries. Black holes are regions of space where gravity is so intense that nothing, not even light, can escape their grasp. At their center lies the singularity, a point of infinite density where the laws of physics as we know them break down. For decades, physicists thought of black holes as cosmic vacuums, swallowing everything that came too close and locking it away forever. But in the 1970s, Stephen Hawking made a startling discovery. Black holes aren't entirely black. They emit a faint glow of radiation, now known as Hawking radiation, and over time, this causes them to slowly evaporate. It was a revelation that connected quantum mechanics to the physics of black holes, opening up a new realm of possibilities and puzzles. Here's how it works. According to quantum mechanics, empty space isn't truly empty. Instead, it's a seething sea of virtual particles that pop in and out of existence, borrowing energy from the vacuum before annihilating each other. When this happens near the event horizon of a black hole, the point of no return, something extraordinary can occur. One of the virtual particles might fall into the black hole while the other escapes into space. The escaping particle carries away energy, effectively stealing it from the black hole and causing it to lose mass over time. This gradual loss of energy is what we call Hawking radiation, and it means that black holes aren't eternal. They slowly shrink and eventually vanish. But this raises a profound question. What happens to all the information that falls into a black hole? In classical physics, information is never truly lost, it's just transformed. But if a black hole evaporates completely, leaving behind only Hawking radiation, it seems like the information about everything it swallowed would be erased forever. This is the black hole information paradox, and it pits the principles of quantum mechanics against those of general relativity. Quantum mechanics insists that information must be conserved, while general relativity suggests it's lost in the singularity. Resolving this paradox is one of the biggest challenges in modern physics, and it has led to some truly mind-bending theories. One of the most provocative ideas is the firewall hypothesis. Imagine falling into a black hole. According to classical physics, you wouldn't feel anything special as you crossed the event horizon, at least not until you were torn apart by the black hole's immense gravity. But the firewall hypothesis suggests that instead of a smooth passage, you'd encounter a blazing wall of energy at the event horizon, incinerating you instantly. This would preserve the information falling into the black hole, but it would also contradict Einstein's theory of general relativity, which predicts no such barrier. It's a radical idea, and it highlights just how much we still have to learn about the interplay between quantum mechanics and gravity. The search for answers has led physicists to explore even more exotic concepts such as string theory and loop quantum gravity. These theories attempt to unify quantum mechanics and general relativity, offering potential solutions to the information paradox and other mysteries of black holes. For example, some researchers propose that information isn't actually lost but is instead encoded on the black hole's event horizon, like a cosmic hologram. Others suggest that black holes might not have singularities at all, that quantum effects could prevent matter from collapsing to infinite density. These ideas are still speculative, but they're pushing the boundaries of our understanding. What makes this quest so exciting is that it's not just about black holes, it's about the fundamental nature of reality. Black holes are cosmic laboratories, places where the laws of physics are stretched to their limits. By studying them, we're not only unraveling their mysteries, we're also uncovering clues about how space, time, and information work at the deepest level. And as we continue to explore, we're led to an even bigger question. What happens when we combine quantum mechanics with gravity on a universal scale? That's where the search for a theory of quantum gravity begins, a journey that could rewrite the rules of the cosmos. Now, let's turn our attention to one of the most ambitious quests in modern physics, the search for a theory of quantum gravity. At the heart of this pursuit is a fundamental question: how can we reconcile the two most successful theories in science, quantum mechanics and general relativity? Quantum mechanics governs the behavior of the smallest particles, revealing a world of probabilities and uncertainties. General relativity, on the other hand, describes the universe on the largest scales, where gravity shapes the fabric of space and time. Both theories have been tested and confirmed countless times, yet they seem to operate in entirely different realms. and when we try to bring them together, especially in extreme environments like black holes or the early universe, they clash in spectacular ways. This is where quantum gravity comes in, a framework that could finally unite these two pillars of physics. One of the leading candidates for quantum gravity is string theory. Imagine if the fundamental building blocks of the universe weren't point-like particles but tiny, vibrating strings. These strings, each billions of times smaller than an atom, would oscillate at different frequencies, giving rise to the various particles and forces we observe. String theory is elegant in its simplicity, but it's also extraordinarily complex, requiring the existence of extra dimensions beyond the three we experience. In some versions of the theory, there are as many as 10 or 11 dimensions, curled up so tightly that we can't perceive them. While string theory remains unproven, it offers a tantalizing possibility: a universe where all forces, including gravity, emerge from the same underlying framework. Another promising approach is loop quantum gravity. Instead of strings, this theory proposes that space itself is made up of tiny, discrete loops. Think of them as the fabric of reality woven together at the smallest scales. These loops form a kind of quantum network, creating a structure that's both continuous and granular. One of the most intriguing predictions of loop quantum gravity is that space-time isn't smooth and infinite but has a finite, quantized structure. This could resolve some of the paradoxes that arise when we try to apply quantum mechanics to black holes or the Big Bang. For example, it suggests that singularities, those points of infinite density, might not exist, replaced instead by a quantum bounce that prevents collapse. Both string theory and loop quantum gravity aim to solve the same problem, but they approach it from different angles. String theory tries to unify all forces under one elegant mathematical framework, while loop quantum gravity focuses on quantizing space itself. Despite their differences, both theories share a common goal: to describe the universe in a way that works at every scale, from the tiniest particles to the vastness of space-time. But the road to quantum gravity is fraught with challenges. These theories are incredibly difficult to test, as their effects only become apparent at scales far beyond our current technological reach. Yet the stakes are enormous. A successful theory of quantum gravity wouldn't just bridge the gap between quantum mechanics and relativity. It would revolutionize our understanding of reality itself. What makes this quest so exciting is that it's not just about solving equations or building models. It's about reimagining the very fabric of the universe. Quantum gravity challenges us to think about space and time in entirely new ways. Are they continuous, or do they have a granular structure? Are there hidden dimensions we can't see? And what happens to the laws of physics at the smallest scales, where gravity and quantum effects collide? These are the kinds of questions that keep physicists up at night, and the answers could change everything we know about the cosmos. As we continue to explore these ideas, we're led to another profound mystery: the role of quantum mechanics in the early universe. What if the Big Bang wasn't a singular event but the result of quantum fluctuations? And how did the universe transition from a quantum soup to the structured cosmos we see today? These questions take us back to the very beginning of everything, where the quantum and the cosmic meet in ways we're only beginning to understand. But that's a story for the next chapter of this quantum journey. Let's take a step back, way back to the very beginning of everything. The Big Bang is often described as the moment the universe burst into existence, a cosmic explosion that set the stage for all we see today. But what if that moment wasn't as straightforward as it sounds? What if the seeds of the universe were sown not by some grand, singular event, but by the tiniest, most unpredictable quantum fluctuations? This is where quantum mechanics steps in, reshaping our understanding of how everything began. In the classical view of the Big Bang, the universe starts as an infinitely dense, infinitely hot singularity. But when we apply the rules of quantum mechanics, the story changes. At the quantum level, nothing is ever perfectly still or perfectly predictable. Even in a vacuum, particles flicker in and out of existence, a phenomenon known as quantum fluctuations. These tiny, random changes in energy might seem insignificant, but in the earliest moments of the universe, they could have set off a chain reaction that shaped the cosmos as we know it. It's a bit like a single pebble starting an avalanche, small actions with enormous consequences. One of the most compelling ideas to emerge from this line of thinking is cosmic inflation. According to this theory, the universe underwent an exponential expansion in the first fraction of a second after the Big Bang. But what drove this rapid expansion? Quantum fluctuations, these tiny ripples in the fabric of space-time, acted as the seeds for the large-scale structure of the universe. Over billions of years, these ripples grew into the galaxies, stars, and planets we see today. In other words, the universe's grand architecture might trace its origins back to the smallest, most fleeting quantum events. This challenges our classical understanding of space and time in profound ways. In the quantum realm, space isn't smooth and continuous, it's dynamic and unpredictable. Time, too, becomes fluid, bending and stretching in ways that defy our everyday experience. The Big Bang, then, isn't just a moment in time, it's a quantum phenomenon shaped by the same rules that govern particles and waves. It's a reminder that even the largest structures in the cosmos have their roots in the smallest scales. But the implications go even further. If quantum fluctuations played such a crucial role in the early universe, could they also explain why the cosmos looks the way it does? Why is the universe so uniform on large scales, yet filled with intricate structures on smaller ones? These are questions that cosmologists are still grappling with, and the answers might lie in the subtle interplay between quantum mechanics and gravity. It's a puzzle that connects the tiniest particles to the vastness of the cosmos, weaving together the threads of quantum theory and general relativity. As we explore these ideas, we're left with a tantalizing possibility that the universe itself might be the result of a quantum event, a fluctuation in the void that grew into everything we know. And if that's the case, what does it mean for our understanding of existence? Are we living in a universe that's just one of many possibilities? This brings us to one of the most mind-bending ideas in modern physics, the multiverse. Could our universe be just one bubble in an infinite cosmic foam, each with its own unique laws of physics? The answer might just redefine what we think is possible. But before we step into the multiverse, let's take a moment to reflect on the journey so far. From the quantum origins of the universe to the intricate dance of particles and forces, we've seen how the smallest scales shape the largest structures. And as we continue to explore, we're reminded that the universe is far stranger and more interconnected than we ever imagined. So, what lies beyond our universe? That's where the next chapter of this cosmic story begins. What if our universe isn't the only one? What if it's just one thread in an infinite tapestry of realities, each with its own unique laws of physics, stars, planets, and perhaps even versions of you? This is the idea of the multiverse, a concept that stretches the boundaries of our imagination and challenges everything we thought we knew about existence. Born from the strange rules of quantum mechanics and the vast mysteries of cosmology, the multiverse suggests that our universe might be just one of countless others, each existing in its own bubble of space and time. It's a theory that's as thrilling as it is mind-bending, and it's reshaping how we think about the cosmos. The seeds of the multiverse idea can be traced back to quantum mechanics, where particles exist in a state of superposition, occupying multiple states at once until observed. But what if this principle doesn't just apply to tiny particles? What if it applies to entire universes? In the many worlds interpretation of quantum mechanics, every possible outcome of a quantum event actually happens, but in a separate parallel universe. For example, if you flip a coin, there's a universe where it lands on heads and another where it lands on tails. Over time, these branching paths create an infinite web of realities, each one slightly or drastically different from our own. But the multiverse isn't just a quantum idea, it's also rooted in cosmology. Take cosmic inflation, the theory that our universe underwent a rapid expansion just after the Big Bang. Some scientists propose that inflation didn't stop everywhere at once. Instead, it might have continued in some regions, creating bubble universes that expand alongside our own. These bubbles could have different physical constants, different laws of nature, and even different dimensions. In this view, the multiverse isn't just a collection of parallel realities, it's a cosmic foam, with each bubble representing a unique universe. The implications of the multiverse are staggering. If this theory is correct, it means that everything we observe in our universe, from the strength of gravity to the number of dimensions, might just be one possibility among an infinite array of others. Some universes might be lifeless, dominated by forces that make stars and planets impossible. Others might be teeming with life, thriving under conditions we can barely imagine. And somewhere out there, in the vast expanse of the multiverse, there might even be a universe where the laws of physics allow for time travel, or where the very concept of space is entirely different. Yet, as fascinating as the multiverse is, it's also deeply controversial. Critics argue that it's untestable after all. How could we ever observe another universe if it's completely disconnected from our own? But proponents counter that the multiverse could leave subtle traces in our universe, clues hidden in the cosmic microwave background or the behavior of particles that hint at the existence of other realities. It's a debate that pushes the limits of science and philosophy, forcing us to ask, what does it mean for something to be real if we can never see or touch it? The multiverse isn't just a scientific idea, it's a profound shift in how we see ourselves in the cosmos. If we're just one universe among countless others, it humbles our place in the grand scheme of things. But it also opens up incredible possibilities. Could we one day communicate with other universes? Could we find evidence of their existence? These questions might sound like science fiction, but they're the kinds of ideas that drive scientists to explore the furthest edges of reality. And as we ponder the mysteries of the multiverse, we're reminded of another quantum marvel, one that's closer to home and yet just as enigmatic. Light, the very fabric of our reality, holds secrets that might just illuminate the connection between the quantum and the cosmic. What happens when we shine a light on the quantum nature of reality? That's where our journey takes us next. Now, let's shine a light on one of the most fundamental yet mysterious aspects of the quantum world: photons. These tiny packets of energy, the building blocks of light, are far more than just the beams that illuminate our world. They are the key to understanding how the universe operates at its most basic level, and their behavior defies everything we thought we knew about space, energy, and reality itself. From the wave-particle duality that baffled early physicists to the groundbreaking experiments that reshaped quantum theory, the story of light is a journey through the heart of quantum mechanics. At the core of this mystery is the dual nature of light. Sometimes light behaves like a wave, spreading out in ripples and creating interference patterns, much like waves on a pond. Other times, it acts like a particle, striking surfaces and knocking electrons loose, as if it were a tiny bullet. This wave-particle duality is one of the most baffling features of quantum mechanics, and it was first brought to light, pun intended, by experiments like the photoelectric effect. In the early 20th century, Albert Einstein used this phenomenon to explain that light isn't just a continuous wave, but is made up of individual particles called photons. This discovery earned him a Nobel Prize and laid the foundation for quantum theory. The photoelectric effect itself is a fascinating demonstration of light's quantum nature. When light shines on a metal surface, it can eject electrons from the material, but only if the light has enough energy. What's remarkable is that this energy doesn't depend on the brightness of the light, only its color or frequency. Even a faint beam of ultraviolet light can eject electrons, while a bright beam of red light might not. This observation was impossible to explain using classical physics, which assumed light was purely a wave. Einstein's insight that light comes in discrete packets of energy, or photons, solved the puzzle and revolutionized our understanding of light, but the story doesn't end there. The double-slit experiment, which we explored earlier, also highlights the strange duality of light. When photons are sent through two slits, they create an interference pattern on a screen, just like waves would. Yet, if you try to measure which slit each photon passes through, the interference pattern disappears and the photons behave like particles. It's as if light knows whether it's being watched, switching between wave-like and particle-like behavior depending on how we observe it. This isn't just a quirk of light, it's a fundamental feature of reality, showing that the universe operates on rules that are far stranger than anything we experience in our everyday lives. This dual nature of light challenges our classical understanding of space and energy. In the classical world, we think of energy as something continuous, like the flow of water in a river. But in the quantum realm, energy comes in discrete chunks or quanta with no in-between states. This quantization is what gives photons their unique properties and forces us to rethink how we describe the universe. It's a reminder that the rules governing the smallest scales are profoundly different from those we're used to. Light also plays a crucial role in some of the most advanced technologies of our time. From lasers that power everything from medical devices to fiber optic communication, to solar panels that harness photons to generate electricity, the quantum properties of light are at the heart of modern innovation. Even in the realm of quantum computing, photons are being explored as a way to transmit information with unprecedented speed and security. It's a testament to how deeply quantum mechanics is woven into the fabric of our technological world. As we explore the quantum nature of light, we're led to an even deeper question. What is light really? Is it a wave, a particle, or something else entirely? The answer lies in the concept of quantum fields, the invisible frameworks that permeate the universe and give rise to particles like photons. These fields aren't just abstract ideas, they're the foundation of reality itself, shaping everything from the smallest particles to the vast expanse of the cosmos. And as we delve into the nature of quantum fields, we'll uncover even more astonishing truths about how the universe works. At the heart of every particle, every force, and every interaction in the universe lies something far more fundamental: quantum fields. These invisible, all-encompassing frameworks aren't just abstract ideas, they're the very fabric of reality itself. Think of them as the stage on which the cosmic play unfolds, a dynamic, ever-shifting network that gives rise to everything we see, touch, and experience. From the photons that make up light to the quarks that form the building blocks of matter, every particle emerges from the vibrations and fluctuations of these fields. It's a concept that transforms our understanding of space and matter, revealing a universe that's far more interconnected and vibrant than we ever imagined. So, what exactly is a quantum field? Imagine a vast, invisible ocean stretching across the entire universe. Within this ocean, waves rise and fall, creating ripples that travel through space. These ripples aren't made of water, they're fluctuations in the quantum field, tiny disturbances that manifest as particles. For example, when the electromagnetic field ripples, it produces photons, the particles of light. Similarly, the electron field gives rise to electrons, while the Higgs field, yes, the same one that gives particles mass, creates Higgs bosons. Every type of particle we know corresponds to a specific quantum field, vibrating in its own unique way. It's as if the universe is a symphony, with each field playing its own note to create the rich tapestry of reality. But here's where it gets even more fascinating. These fields aren't static, they're constantly in motion, interacting with one another in intricate and sometimes unpredictable ways. When two particles collide, say an electron and a photon, they're actually interacting through their underlying fields. The electron field and the electromagnetic field exchange energy, creating new ripples that can produce different particles or alter the state of existing ones. This dance of fields is what drives the fundamental forces of nature, from the electromagnetic force that powers your smartphone to the strong nuclear force that holds atomic nuclei together. It's a dynamic, ever-changing process that shapes the behavior of everything in the cosmos. The implications of quantum fields are profound. They suggest that what we perceive as empty space isn't empty at all. It's teeming with activity, a seething sea of energy and potential. Even in a perfect vacuum where no particles are present, the fields are still there, fluctuating and interacting in ways we can't see. This is the so-called quantum vacuum, a state of pure potential where particles can pop into existence, borrow energy, and vanish again in the blink of an eye. It's a reminder that the universe is far more active and interconnected than our everyday experience suggests. Quantum fields also challenge our classical notions of space and matter. In the classical world, we think of space as a fixed, empty stage and matter as solid, distinct objects. But in the quantum realm, space is a dynamic, energetic field, and matter is just a manifestation of its vibrations. This blurring of boundaries forces us to rethink what it means for something to exist. Is an electron a particle, or is it a ripple in the electron field? The answer, it seems, is both and neither. Quantum fields reveal a universe that's far more fluid and interconnected than we ever imagined. As we delve deeper into the nature of quantum fields, we're led to an even more intriguing question. What does this mean for the quantum nature of matter itself? If particles are just vibrations in fields, what does that tell us about the fundamental building blocks of the universe? This takes us into the heart of the quantum world, where matter behaves in ways that defy our intuition and challenge our understanding of reality. But that's a story for the next chapter of this quantum journey. Now, let's zoom in on the atomic scale, where the rules of quantum mechanics transform the way we think about matter itself. At this level, the familiar states of solids, liquids, and gases take on a whole new dimension, governed by principles that defy our everyday experience. Quantum mechanics doesn't just describe the behavior of individual particles. It reshapes how entire systems of matter interact, creating phenomena that challenge our classical understanding of space and energy. From the strange world of superconductivity to the mind-bending properties of Bose-Einstein condensates, the quantum behavior of matter reveals a universe far more dynamic and interconnected than we ever imagined. Take superconductivity, for example. In the classical world, when electricity flows through a wire, it encounters resistance, losing energy as heat. But in certain materials, when cooled to extremely low temperatures, something extraordinary happens. The electrical resistance drops to zero, and the material becomes a superconductor, allowing electricity to flow without any loss of energy. This isn't just a slight improvement, it's a complete transformation of how matter behaves. The key lies in the quantum nature of electrons. In a superconductor, electrons pair up in a way that allows them to move through the material as a single, coherent wave, bypassing the usual obstacles that cause resistance. This quantum dance of electrons isn't just a scientific curiosity. It's the foundation of technologies like magnetic resonance imaging (MRI) and maglev trains, which rely on superconductors to function. But superconductivity isn't the only quantum marvel at the atomic scale. Enter Bose-Einstein condensates, a state of matter so strange that it was once thought to be purely theoretical. In the mid-1920s, Satyendra Nath Bose and Albert Einstein predicted that under certain conditions, atoms could lose their individuality and merge into a single quantum entity. It wasn't until the 1990s that scientists were able to create this state in the lab by cooling atoms to temperatures just above absolute zero. At these frigid temperatures, the atoms slow down so much that their quantum waves overlap, forming a single, unified wave that behaves as one giant particle. This bizarre state of matter, where individual atoms seem to disappear into a collective quantum soup, challenges our classical notions of how matter should behave. It's as if the atoms have decided to abandon their personal identities and become one with the universe. These quantum phenomena don't just redefine our understanding of matter, they also challenge our perception of space. In the classical world, space is the stage where matter moves and interacts. But in the quantum realm, space itself becomes a dynamic participant, shaping the behavior of particles and systems in ways we're only beginning to understand. For instance, in a Bose-Einstein condensate, the overlapping quantum waves of atoms create a kind of quantum fluid that can flow without friction or viscosity. This fluid doesn't just fill space, it transforms it, creating a medium where quantum effects dominate and classical physics falls short. It's a vivid reminder that space isn't just an empty backdrop, it's an active, integral part of the quantum world. What's truly astonishing is how these discoveries are reshaping technology. Superconductors are already revolutionizing fields like energy transmission and medical imaging, while Bose-Einstein condensates are opening up new possibilities for precision measurements and quantum simulations. But the implications go far beyond practical applications. These phenomena force us to confront fundamental questions about the nature of matter and space. Are particles truly separate entities, or are they part of a larger, interconnected system? And if quantum effects can create such dramatic transformations at the atomic scale, what might they reveal about the universe as a whole? As we explore these questions, we're led to an even more transformative idea: the potential of quantum computing. If quantum mechanics can redefine the behavior of matter and space, could it also revolutionize the way we process information? This is where the quantum journey takes us next, into a world where computation isn't limited by classical rules, but instead harnesses the strange and powerful principles of the quantum realm. Imagine a computer so powerful that it could solve problems in seconds, problems that would take even the fastest supercomputers thousands of years to crack. This isn't science fiction, it's the promise of quantum computing, a revolutionary technology that taps into the strange and wondrous rules of the quantum world. Unlike classical computers, which rely on bits that can be either a 0 or a 1, quantum computers use qubits, quantum bits, that can exist in multiple states at once, thanks to the phenomenon of superposition. This ability to be both 0 and 1 simultaneously allows quantum computers to perform an astronomical number of calculations in parallel, unlocking computational power that defies imagination. But superposition is just the beginning. Quantum computers also harness entanglement, that mysterious connection between particles we explored earlier. When qubits become entangled, the state of one instantly influences the state of another, no matter how far apart they are. This creates a kind of quantum teamwork where qubits work together in ways that classical bits simply can't. The result, a machine that can tackle problems of staggering complexity, From simulating molecular interactions for drug discovery to optimizing global supply chains and cracking cryptographic codes that secure our digital world. It's as if quantum computing lifts the lid on a hidden dimension of information processing, one that's been waiting just beneath the surface of classical physics. Yet, as groundbreaking as this technology is, it's not without its challenges. Quantum systems are incredibly delicate. Even the slightest disturbance, a stray photon, a vibration, or a fluctuation in temperature can cause qubits to lose their quantum state, a problem known as decoherence. To combat this, quantum computers must operate in ultra-controlled environments, often at temperatures colder than deep space. And even then, building a machine with enough qubits to perform meaningful computations is a monumental task. Despite these hurdles, companies and researchers around the world are racing to develop quantum computers, pushing the boundaries of what's possible and redefining the future of technology. The potential applications of quantum computing are vast. Imagine designing new materials with unprecedented strength or efficiency, revolutionizing industries from aerospace to renewable energy. Or consider the impact on artificial intelligence, where quantum algorithms could process and analyze data in ways that make today's AI systems seem rudimentary. In medicine, quantum simulations could unlock the secrets of complex proteins, leading to breakthroughs in treatments for diseases like Alzheimer's or cancer. And in cryptography, quantum computers could both break existing codes and create unbreakable ones, transforming how we secure information in the digital age. But with great power comes great responsibility. The rise of quantum computing raises profound ethical questions, from the potential misuse of its capabilities to the societal impacts of such a transformative technology. What happens when quantum computers can crack the encryption that protects our most sensitive data? How do we ensure that this technology is developed and used in ways that benefit humanity as a whole? These are questions we can't afford to ignore, and they lead us to the next chapter of this quantum journey, the ethical implications of these extraordinary discoveries. How do we navigate the moral and societal challenges that come with unlocking the secrets of the quantum world? The answers might just shape the future of our species. As we stand on the brink of a quantum revolution, the incredible potential of quantum mechanics comes with profound ethical questions. The same technologies that promise to transform medicine, energy, and computing also carry the potential for misuse, raising concerns about how we navigate the fine line between progress and responsibility. Quantum mechanics isn't just about understanding the universe, it's about shaping it. And with that power comes a critical question: how do we ensure that these discoveries benefit humanity without causing harm? Let's start with quantum computing. While the ability to solve problems at unprecedented speeds is exhilarating, it also poses significant ethical challenges. One of the most pressing concerns is cybersecurity. Quantum computers have the potential to break the encryption systems that protect everything from your bank account to national security communications. While this could be a boon for cracking codes and uncovering hidden threats, it also opens the door to misuse. Imagine a world where personal data, financial systems, and even government secrets are vulnerable to quantum-powered hacking. The stakes couldn't be higher, and the race is on to develop quantum-resistant encryption before these threats become reality. But the ethical dilemmas don't stop there. Quantum technologies also have potential military applications, from advanced surveillance systems to quantum-enhanced weapons. While these innovations could bolster national security, they also risk escalating global tensions and creating new arms races. The idea of quantum warfare, where information is weaponized and decision-making is accelerated to near instantaneous speeds, isn't science fiction. It's a scenario that policymakers and scientists must grapple with today. The challenge lies in balancing the pursuit of scientific breakthroughs with the need to prevent their misuse, ensuring that quantum advancements serve as tools for peace rather than conflict. Beyond security and warfare, there's also the question of access. Quantum technologies are complex and expensive to develop, which could lead to a widening gap between those who can harness their power and those who cannot. Will quantum computing become a privilege for the few, or will it be democratized to benefit all of humanity? This isn't just a technical challenge, it's a moral one. Ensuring equitable access to quantum innovations requires intentional efforts to bridge the gap, from funding research in developing nations to creating educational programs that empower the next generation of quantum scientists. At the heart of these ethical considerations is a deeper, more philosophical question. How do we define responsible innovation? Science has always been about pushing boundaries, but history has shown that progress without foresight can lead to unintended consequences. Take, for example, the development of nuclear technology. While it brought us clean energy and medical advancements, it also gave rise to weapons of mass destruction. Quantum mechanics presents us with a similar crossroads. Will we use these discoveries to uplift humanity, or will we repeat the mistakes of the past? The good news is that the scientific community is increasingly aware of these ethical challenges. Organizations and researchers are working to establish guidelines for responsible quantum development, emphasizing transparency, collaboration, and public engagement. By involving diverse voices from ethicists to policymakers to everyday citizens, we can ensure that quantum technologies are shaped by a collective vision of progress, one that prioritizes the well-being of society as a whole. As we reflect on the ethical dimensions of quantum mechanics, we're reminded that science doesn't exist in a vacuum. It's deeply intertwined with the values, priorities, and choices of humanity. The discoveries we make today will shape the world of tomorrow, and it's up to us to decide what kind of future we want to create. This brings us to the next frontier of quantum research, a future filled with possibilities, challenges, and the promise of unlocking even deeper mysteries of the universe. What lies ahead in the world of quantum exploration? That's where our journey takes us next. The future of quantum research is not just a continuation of what we know, it's a leap into uncharted territory, where the boundaries of technology and our understanding of reality are being redrawn. At the forefront of this exploration are quantum networks, a revolutionary concept that could transform how we communicate and share information. Imagine a global internet powered by the principles of quantum entanglement, where data is transmitted instantaneously across vast distances, completely secure from interception or hacking. Unlike classical networks which rely on bits that can be copied or intercepted, quantum networks use qubits whose states are inherently linked through entanglement. This means that any attempt to eavesdrop would instantly alter the information, alerting users to the breach. Scientists are already making strides in this area, with quantum communication satellites and ground-based experiments demonstrating the feasibility of such networks. One day, these systems could enable everything from ultra-secure banking to real-time global collaboration on a scale we've never seen before. But the potential of quantum research doesn't stop at communication. Quantum sensors are another groundbreaking innovation poised to revolutionize multiple fields. These devices harness the extreme sensitivity of quantum systems to measure things like gravity, magnetic fields, and time with unprecedented precision. For instance, quantum gravimeters could map underground structures with incredible accuracy, aiding in everything from archaeology to earthquake prediction. In medicine, quantum sensors could detect tiny magnetic fields produced by brain activity, offering new insights into neurological disorders. Even in space exploration, quantum sensors could help us detect faint gravitational waves or map the interior of distant planets. The applications are as vast as they are transformative, and researchers around the world are racing to bring these technologies to life. One of the most exciting areas of quantum research is the development of quantum simulators. These are specialized quantum computers designed to model complex systems that are impossible to study with classical methods. For example, they could simulate the behavior of molecules for drug discovery, allowing scientists to test thousands of potential treatments in a fraction of the time. Or they could model the intricate dynamics of climate systems, providing more accurate predictions to combat global warming. Quantum simulators represent a bridge between theory and practice, offering a tangible way to apply the strange rules of quantum mechanics to real-world problems. Yet, for all the promise of these technologies, the journey ahead is filled with challenges. Building practical quantum networks requires overcoming issues like decoherence, where qubits lose their quantum state due to environmental interference. Scaling up quantum sensors and simulators demands breakthroughs in materials science and engineering. And even as we make progress, the theoretical foundations of quantum mechanics continue to evolve. Researchers are exploring ideas like quantum gravity, which seeks to reconcile quantum mechanics with general relativity, and quantum field theory, which delves into the fundamental nature of particles and forces. These aren't just abstract pursuits, they're quests to uncover the deepest truths about the universe. As we push the boundaries of quantum research, we're not just developing new technologies, we're also reshaping our understanding of reality itself. The strange behaviors of quantum particle superposition, entanglement, and tunneling are forcing us to rethink long-held assumptions about space, time, and existence. And this brings us to a profound question. What does it all mean for us as observers and participants in this quantum universe? The philosophical implications of quantum mechanics are as fascinating as the science itself, challenging us to reconsider our place in the cosmos. But that's a story for the next chapter of this quantum journey. What does it mean to truly exist? For centuries, philosophers have grappled with this question, crafting theories about reality, consciousness, and the nature of being. But quantum mechanics has thrown a wrench into those classical ideas, forcing us to rethink some of the most fundamental assumptions about existence itself. At the heart of this philosophical revolution is a simple yet profound question. Is reality something absolute and unchanging, or is it shaped by the act of observation? The strange behavior of quantum particles suggests that the answer might be far more complex and far more fascinating than we ever imagined. Let's start with the observer effect, one of the most intriguing aspects of quantum mechanics. In the quantum world, particles don't have definite properties until they're measured. Instead, they exist in a superposition of states, multiple possibilities coexisting at once. It's only when an observer takes a measurement that the particle chooses a single state, collapsing the wave function. This raises a profound question. Does the act of observation create reality? Some interpretations of quantum mechanics, like the Copenhagen interpretation, suggest that the observer plays an active role in shaping the outcome of quantum events. In this view, reality isn't something fixed and external. It's a dynamic interplay between the observer and the observed. It's as if the universe is a cosmic canvas, and we, the observers, are the artists painting reality with every measurement we make. This idea challenges traditional philosophical frameworks, particularly the notion of objective reality. For centuries, philosophers like René Descartes and Immanuel Kant argued that reality exists independently of our perception, an external world that we observe but do not create. Quantum mechanics, however, suggests that reality might be more subjective, shaped by the interactions between observers and the quantum systems they study. This doesn't mean that reality is an illusion, but rather that it's co-created, a collaborative effort between the quantum world and those who observe it. It's a perspective that blurs the line between the observer and the observed, forcing us to reconsider what it means to exist in a universe that's fundamentally interconnected. But the philosophical implications don't stop there. Quantum mechanics also raises questions about causality, the idea that every event has a cause. In the classical world, we're used to thinking of cause and effect as a straightforward chain of events. But in the quantum realm, particles can behave in ways that defy this linear logic. Take quantum entanglement, for example. When two particles become entangled, the state of one instantly influences the state of the other, no matter how far apart they are. This instantaneous connection seems to bypass the constraints of space and time, challenging our classical understanding of causality. Some philosophers argue that quantum mechanics hints at a deeper, more holistic reality, where everything is interconnected and causality operates on a level we don't yet fully understand. These ideas have profound implications for our understanding of existence. If reality is shaped by observation and causality isn't as straightforward as we thought, then the universe might be far more fluid and dynamic than we ever imagined. It suggests that existence isn't a static, unchanging state, but a process, a continuous unfolding of possibilities. This perspective resonates with certain philosophical traditions, such as Buddhism, which views reality as interdependent and ever-changing. Quantum mechanics, in a sense, bridges the gap between science and philosophy, offering new ways to explore age-old questions about the nature of being. But what does this mean for us as individuals? If we're active participants in shaping reality, how does that impact our sense of self and our place in the cosmos? These questions touch on the intersection of quantum mechanics and consciousness, a topic that's as controversial as it is fascinating. Some theorists propose that consciousness itself might play a role in collapsing the wave function, making it a fundamental aspect of reality. While this idea remains speculative, it invites us to consider how deeply intertwined we are with the universe, not just as passive observers but as co-creators of reality. As we delve into these philosophical questions, we're reminded that quantum mechanics isn't just a scientific framework, it's a lens through which we can explore the deepest mysteries of existence. It challenges us to rethink not only how the universe works, but also who we are within it. And as we continue this journey, we find ourselves at the intersection of science and art, where the abstract principles of quantum mechanics inspire creativity and imagination. How do artists interpret the strange and beautiful world of quantum physics? That's where our exploration takes us next. Art has always been a mirror to the human experience, reflecting our deepest questions, fears, and wonders. But what happens when artists turn their gaze to the quantum realm? A world that defies intuition and challenges the very nature of reality. The result is quantum art, a mesmerizing fusion of science and creativity that explores the unseen, the abstract, and the profoundly mysterious. From paintings that capture the duality of particles to music that echoes the rhythms of quantum fields, creators are using the principles of quantum mechanics to push the boundaries of what art can be. These works don't just inspire, they challenge us to see the universe in a whole new way. One striking example of quantum art is the work of physicist-turned-artist Julius von Bismarck. His installations use light and motion to create visual representations of quantum phenomena, such as superposition and entanglement. In one piece, a beam of light splits into multiple paths, creating an interference pattern that mimics the behavior of particles in the double-slit experiment. Viewers don't just see the art, they experience it, becoming part of the quantum dance themselves. It's a powerful reminder that the strange rules of the quantum world aren't just abstract ideas. They're part of the fabric of reality, shaping everything from the smallest particles to the grandest works of art. But quantum art isn't limited to the visual realm. Musicians, too, are finding inspiration in the rhythms and harmonies of the quantum world. Composer Jonathan Harvey, for instance, created a piece titled Mortuos Plango Vivos Voco, which uses the resonant frequencies of a cathedral bell to explore the concept of quantum vibrations. The music shifts and fluctuates, creating a soundscape that feels both ancient and futuristic, grounded and ethereal. It's as if Harvey has tapped into the universal hum of quantum fields, translating their vibrations into a language we can hear and feel. This fusion of sound and science invites us to listen to the universe in a way we've never done before. Literature, too, has embraced the quantum revolution. Writers like Philip Pullman and Ted Chiang weave quantum concepts into their stories, crafting narratives that blur the line between science and imagination. In Pullman's His Dark Materials trilogy, for example, the idea of parallel universes, a concept rooted in quantum mechanics, plays a central role in the plot. These stories don't just entertain, they challenge us to think about the nature of reality, asking questions that resonate long after the final page is turned. Through literature, quantum mechanics becomes more than a scientific theory. It becomes a lens through which we explore the human condition. What makes quantum art so compelling is its ability to make the invisible visible. Through paintings, music, and stories, artists give form to the abstract, helping us grasp concepts that might otherwise feel intangible. A painting of entangled particles, for instance, can evoke the eerie connection between two objects separated by vast distances. A piece of music inspired by quantum vibrations can make us feel the pulse of the universe itself. These works don't just reflect the quantum world, they invite us to step inside it, to see, hear, and feel the strange beauty of a reality that defies our everyday experience. But quantum art isn't just about understanding science, it's about expanding our perception of creativity itself. By drawing inspiration from the quantum realm, artists are breaking free from traditional constraints, exploring new forms of expression that challenge our notions of space, time, and existence. This fusion of science and art reminds us that creativity isn't confined to one discipline. It's a universal force, as fundamental to the cosmos as the particles that make it up. As we marvel at these quantum-inspired creations, we're reminded that the impact of quantum mechanics extends far beyond the laboratory. It's shaping how we think, how we create, and how we see ourselves in the universe. And this brings us to the next chapter of this journey, the cultural impact of quantum discoveries. How has the quantum revolution influenced the way we live, work, and dream? The answers might just redefine what it means to be human in a quantum world. Quantum mechanics isn't just a field of science, it's a cultural phenomenon that has seeped into every corner of our lives, from the stories we tell to the way we think about the universe. It's reshaped the narrative of science fiction, inspired blockbuster films, and even influenced the way we teach and understand the world. Think about it. How many times have you seen a movie or read a book where characters teleport across space, exist in parallel universes, or manipulate time? These ideas, once the domain of theoretical physics, have become staples of popular culture, sparking imaginations and challenging audiences to think beyond the limits of classical reality. But the influence of quantum mechanics goes far beyond entertainment. It's reshaping education, technology, and even how we perceive the boundaries of what's possible. Take science fiction, for example. Quantum mechanics has become a playground for storytellers, offering a treasure trove of bizarre and mind-bending concepts to explore. From the parallel universes of The Man in the High Castle to the time loops of Edge of Tomorrow, quantum ideas have become central to some of the most iconic narratives of our time. Even in films like Ant-Man, where the hero shrinks to the quantum scale, we see a playful yet thought-provoking exploration of how the rules of reality change at the tiniest levels. These stories don't just entertain, they introduce audiences to the strange and wonderful world of quantum mechanics, making complex ideas accessible and exciting. But quantum culture isn't limited to fiction. It's also transforming how we educate the next generation. In classrooms around the world, teachers are using quantum concepts to inspire curiosity and critical thinking. Gone are the days when physics was just about pulleys and inclined planes. Today, students are learning about superposition, entanglement, and the uncertainty principle ideas that challenge them to think outside the box and question the nature of reality itself. Educational tools like quantum simulators and interactive apps are bringing these abstract concepts to life, making them tangible and engaging for learners of all ages. It's a shift that's not just preparing students for careers in science and technology, it's equipping them with the mindset to navigate an increasingly complex world. The impact of quantum mechanics is also felt in the technologies we use every day. From the lasers in our smartphones to the encryption that protects our online transactions, quantum principles are woven into the fabric of modern life. And as quantum computing and communication technologies advance, we're on the brink of a revolution that could redefine everything from healthcare to finance. But with these advancements comes a challenge. How do we ensure that the public understands and embraces these technologies? Quantum mechanics is notoriously difficult to explain, and its abstract nature can make it feel inaccessible to those without a scientific background. This has led to a growing need for effective science communication, a way to bridge the gap between the quantum world and everyday understanding. This brings us to one of the most pressing challenges in the quantum revolution: communication. How do we translate the strange and counterintuitive principles of quantum mechanics into language that resonates with a broader audience? It's a question that scientists, educators, and communicators are grappling with as they work to demystify this complex field. From documentaries and podcasts to public lectures and interactive exhibits, efforts are being made to make quantum concepts more relatable, but the task isn't easy. Quantum mechanics defies our everyday experience, challenging us to rethink fundamental ideas about space, time, and reality. Communicating these ideas requires not just clarity, but creativity, finding ways to connect with people on an emotional and intellectual level. As we navigate this challenge, we're reminded of the profound impact that quantum mechanics has had on our culture and society. It's not just a scientific theory, it's a lens through which we see the world, a source of inspiration and innovation that continues to shape our thoughts, our technologies, and our stories. But as we strive to share these ideas with a wider audience, we're also confronted with another question. How do we ensure that the next generation of thinkers and creators is prepared to carry this quantum revolution forward? This leads us to the next chapter of this journey, the future of quantum education and the role of creativity in shaping the quantum age. How can we inspire the next Einstein, the next Feynman, or even the next quantum artist? The answers might just redefine how we learn, create, and imagine in a quantum world. Quantum mechanics is undeniably fascinating, but let's be honest, it's also incredibly hard to explain. How do you take something as abstract as a particle that's both here and there, or a pair of particles that communicate instantaneously across galaxies, and make it understandable, let alone relatable to someone without a physics degree? This is the challenge of science communication, and it's never been more important than in the age of quantum discoveries. As we uncover more about the quantum world, we're faced with a critical question. How do we share these groundbreaking ideas in a way that sparks curiosity rather than confusion? One of the biggest hurdles in explaining quantum mechanics is its sheer strangeness. Unlike the predictable cause and effect world we experience every day, the quantum realm operates on rules that seem to defy logic. Concepts like superposition, entanglement, and wave-particle duality don't just challenge our intuition, they upend it. For many, the first reaction to hearing about these phenomena is often a mix of awe and skepticism. How can a particle be in two places at once? What does it mean for particles to be entangled? These are fair questions, and they highlight the need for clear, engaging explanations that don't oversimplify but still make the science accessible. So how do we bridge this gap? One effective strategy is storytelling. By framing quantum concepts within relatable narratives, we can help people connect with the ideas on a human level. Take Schrödinger's cat, for example. While the thought experiment is famously bizarre, a cat that's both alive and dead until observed, it's also a powerful metaphor for the unpredictability of quantum systems. By grounding abstract ideas in familiar scenarios, we make them easier to grasp. Similarly, analogies can be incredibly helpful. Describing quantum entanglement as a pair of dice that always land on matching numbers, no matter how far apart they are, gives people a tangible way to visualize the phenomenon. Visuals are another essential tool in the science communicator's toolkit. Quantum mechanics deals with phenomena that are invisible to the naked eye, so diagrams, animations, and even interactive simulations can bring these concepts to life. Imagine a video showing how particles create an interference pattern in the double-slit experiment, or an animation illustrating how quantum tunneling works. These visual aids don't just explain the science, they make it engaging, helping viewers see the quantum world in action. But effective communication isn't just about simplifying complex ideas, it's also about fostering a sense of wonder. Quantum mechanics isn't just a collection of abstract theories, it's a window into the fundamental nature of reality. By emphasizing the beauty and mystery of the quantum world, we can inspire curiosity and excitement, even in those who might not consider themselves science people. This approach isn't about dumbing things down, it's about inviting people into the conversation, showing them that the quantum realm isn't just for physicists in lab coats. It's for anyone who's ever looked up at the stars and wondered how the universe works. The importance of this effort can't be overstated. As quantum technologies like computing, encryption, and sensing become more integrated into our lives, public understanding of these advancements will be crucial. Misinformation and misunderstanding can lead to fear or skepticism, hindering progress and innovation. On the other hand, a society that's informed and engaged with quantum science is better equipped to make thoughtful decisions about its applications and implications. This is why science communication isn't just a nice to have, it's a necessity. As we work to make quantum mechanics more accessible, we're reminded that the journey of discovery isn't just about answering questions, it's about asking them. Every explanation, every metaphor, every visualization is an invitation to explore, to wonder, and to connect with the profound mysteries of the universe. And this brings us to a deeply personal dimension of quantum discoveries, how they change the way we see ourselves and our place in the cosmos. What happens when the abstract principles of quantum mechanics collide with the human experience? That's where our journey takes us next. What if the most profound discoveries in science didn't just change how we understand the universe, but also how we understand ourselves? Quantum mechanics, with all its strange and wondrous phenomena, doesn't just challenge our ideas about space and time. It invites us to reflect on our place in the cosmos. When you dive into the quantum world, you're not just learning about particles and waves, you're stepping into a reality that's fluid, interconnected, and deeply mysterious. And as you explore, something remarkable happens. Your perspective on life, on existence, and on what it means to be human begins to shift. Think about it. For centuries, we've viewed the universe as a collection of separate objects, governed by fixed laws and predictable outcomes. But quantum mechanics tells a different story. It reveals a universe where particles can exist in multiple states at once, where observation shapes reality, and where the boundaries between objects blur in ways that defy intuition. These ideas don't just belong to the realm of physics, they resonate with deeper questions about our own lives. How often do we see the world in black and white when the truth is far more nuanced? How much of what we perceive as fixed and unchanging is actually shaped by our own perspectives? Quantum mechanics invites us to embrace uncertainty, to see the world not as a static stage but as a dynamic, ever-evolving process. This shift in perspective can be incredibly liberating. In a world that often feels rigid and deterministic, quantum mechanics reminds us that there's room for possibility, for creativity, and for change. It's a reminder that the choices we make, the observations we take, and the connections we forge all play a role in shaping our reality. In a sense, we're not just passive observers of the universe, we're active participants, co-creators of the world we experience. And that realization can be both empowering and humbling. It challenges us to take responsibility for our actions, to approach life with curiosity and openness, and to recognize the profound interconnectedness of all things. But quantum mechanics doesn't just change how we see the world, it also changes how we see ourselves. As we grapple with concepts like superposition and entanglement, we're forced to confront the limits of our understanding. We're reminded that there's so much we don't know, so much that lies beyond the boundaries of our current knowledge. And yet, this uncertainty isn't something to fear, it's something to embrace. It's a call to stay curious, to keep asking questions, and to remain open to the possibility that the universe is far stranger and more beautiful than we ever imagined. These reflections aren't just abstract musings, they're deeply personal. For many, learning about quantum mechanics is a transformative experience, one that sparks a sense of wonder and awe. It's like peering through a keyhole into a hidden dimension where the rules of reality are rewritten and the possibilities are endless. And as we stand on the threshold of this new understanding, we're reminded that the journey of discovery is never truly finished. There's always more to learn, more to explore, and more to marvel at. So, as we near the end of this quantum journey, let's take a moment to reflect on what we've learned. From the bizarre behavior of particles to the mind-bending implications of entanglement and superposition, quantum mechanics has shown us a universe that's far more dynamic and interconnected than we ever imagined. It's a universe that challenges us to rethink our assumptions, to embrace uncertainty, and to see the world with fresh eyes. And as we continue to explore these ideas, we're not just uncovering the secrets of the cosmos, we're also discovering new ways to understand ourselves and our place within it. But our journey doesn't end here. As we bring this exploration to a close, let's take a step back and consider the bigger picture. What does it all mean for us as individuals, as a society, and as a species? How can we take the lessons of quantum mechanics and apply them to our lives, our relationships, and our understanding of the universe? These are the questions we'll explore as we wrap up this extraordinary adventure into the quantum world. As we come to the end of this journey through the quantum realm, let's take a moment to reflect on the extraordinary discoveries we've explored together. From the eerie connection of entangled particles that communicate instantaneously across vast distances, to the mind-bending idea that particles can exist in multiple states at once through superposition, quantum mechanics has shown us a universe far stranger and more interconnected than we ever imagined. We've delved into the mysteries of quantum tunneling, where particles defy classical barriers, and marveled at the concept of quantum fields, the invisible fabric that weaves together the very essence of reality. And we've even ventured into the holographic principle, a theory that suggests our three-dimensional universe might be a projection of information encoded on a two-dimensional surface. Each of these ideas challenges our classical understanding of space, time, and existence itself, inviting us to see the cosmos in a whole new light. What makes these discoveries so profound isn't just their scientific significance, it's the way they force us to question the very nature of reality. Quantum mechanics doesn't just describe the behavior of tiny particles, it reshapes how we think about ourselves and our place in the universe. It reveals a world where observation shapes reality, where particles are deeply interconnected, and where the boundaries of space and time are far more fluid than we once believed. It's a reminder that the universe is not a static, unchanging stage, but a dynamic, ever-evolving process, one that we, as observers and participants, play a role in shaping. As the physicist Richard Feynman once said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." This quote captures the essence of what makes this field so endlessly fascinating. It's not just about finding answers, it's about embracing the questions, the mysteries, and the possibilities. Quantum mechanics invites us to stay curious, to keep exploring, and to remain open to the idea that the universe is far more wondrous than we can ever fully comprehend. So, as we wrap up this exploration, I want to leave you with a thought. The quantum world isn't just a realm of science, it's a source of inspiration. It challenges us to think differently, to see beyond the limits of our everyday experience, and to marvel at the incredible complexity and beauty of the cosmos. And who knows, the next great discovery in quantum mechanics could come from you. Whether you're a scientist, a student, or simply someone with a curious mind, the quantum world is waiting to be explored. If this journey through the quantum realm sparked your curiosity, I'd love to hear your thoughts. What part of quantum mechanics fascinates you the most? Drop your ideas in the comments below. I read everyone. And if you enjoyed this video, don't forget to subscribe and hit that notification bell so you never miss an episode of our mind-expanding adventures. Together, let's keep exploring the mysteries of the universe, one quantum leap at a time. Until next time, stay curious and remember, the cosmos is far stranger and more beautiful than we ever imagined.